All right, this video is going to talk about inverse trig functions and sort of how they're defined and why we get the values that we do when we type them into a calculator. So first of all, over at the left, we've got the graphs of the sine of x, the cosine of x, and the tangent of x. Now, when we talk about an inverse function, remember what basically happens is if we drew a line at y equals x, right, on our graph, right, such as I did on the sine graph there, all of the values, right, that we have need to reflect, if you will, sort of need to reflect over that line, right? Every inverse function is just a reflection of the previous function over the line y equals x. So what's going to basically happen, and I'm just going to grab some of the major points here, is that 0, 0 for the sine of x anyways, for the inverse sine, will still be 0, 0. But where we would normally have been at pi over 2, 1, right, that first maximum that we received, we would also be at 1 pi over 2. So we're going to be up here. It's going to look like a maximum as well, only now where the curve sort of was cupped down, if you will, right, that downward curve, we're going to sort of be cup upwards. If you think about those values, again, we're sort of flipping that over that line y equals x, right? We're changing the curve a little bit. The same thing happens out to the left, okay? But I'm going to come back to that here in just a second. The reason I stopped at that maximum is, remember, there's also a rule that says if an original function can't pass the horizontal line test, which the sine of x definitely cannot, right? We have multiple values that are going to hit that same horizontal line over and over and over as our graph continues infinitely to the right and left, right? We're all real number domain. So this sinusoidal curve just keeps going. Well, if it can hit multiple places, then it doesn't have an inverse function. So what we need to do is restrict our domain a little bit, right? We're going to change that all real numbers domain, and we're going to restrict ourselves from negative pi over 2, right, up to pi over 2. And the reason we would do that is it's the first time we would have had a minimum on the sine graph all the way up to sort of a first maximum. We still get all of those y values from -1 up to +1 before they start to repeat themselves, right, going from 1 back down to -1 or kind of continuing onwards. If I only use that sort of small red squiggle of a graph, well, then I can get an inverse graph here, right, an inverse function graph. Again, what used to be my range will now be my domain. So -1 to 1, right, top to bottom, just became our domain, -1 to 1. But our domain just became our range. So our range for the inverse sine, the values we'll get back, will always be somewhere in between, right, pi over 2 and negative pi over 2. So again, if I go down here, negative pi over 2 on our graph, we plot there. And again, this small squiggle is really all that our function will look like. No arrows, because again, to go upwards, it would have had to sort of swing back to the left, right? Would have been the same periodic function, only going sort of from top to bottom, right? Continuing there, and it wouldn't pass a vertical line test then. It wouldn't be a function. So this is literally it for that graph. Now, we don't graph that a whole lot because it's not the most helpful graph on the planet. Very rarely would we ever use this to shift or stretch or do anything else with it. There are ways to use that inverse sine, or I may as well mention it, what we sometimes call the arc sine. That's another way of representing the inverse sine. Just two ways of saying the same thing. So again, to graph the arc sine, it's going to look like this just little squiggle, right? Cosine sort of works the same way. We're going to restrict ourselves, again, from the first maximum. Now, the nice part is the cosine starts at a high point, and so we just have to go to our first minimum. So if we only graph, again, instead of all real numbers, if we only went from 0 to pi, the range of the arc cosine, therefore, is going to be from 0 to pi. And again, our old range just became our new domain, right? So we're going to put that there. Only, of course, since it's domain, now it deals with x, not y, right? So again, x is going to range between -1 and 1. So again, that same idea happens. X goes from -1 to 1. We go from 0 to pi this time, right? And again, 0, 1 just became 1, 0. -1 used to be at pi, so again, -1 pi. and again, halfway in between. Our curve sort of still stays the same here. It sort of squiggles back there. Again, not the most important squiggle of a graph to know, but just realize if you ever tried to graph the inverse cosine or arc cosine, that's what it would look like. Right? Tangent's kind of nice because, again, it's got an all real numbers domain, avoiding those asymptotes, but it also has an all real numbers range. Right? So again, the domain then of your tangent stays all real numbers. The range stays all real numbers, except for, again, we need to avoid, again, pi over 2 and negative pi over 2, or basically pi over 2n. Well, the nice part is, again, in order to restrict and pass that horizontal line test, the easiest thing to do is just stick to that first curve, right, that we would have of a tangent. But now if we flip that curve, again, it's got to exist between positive and negative pi over 2, and it actually comes out looking almost like a cubed root function with sort of that S curve, but restricted there. Now, the more helpful way to think of these is actually using the unit circle a little bit. And what I always like to think of is if I was graphing an inverse sine or an inverse tangent, notice that those are the two, right, where we're going to be restricted. And actually, I better restrict my range down here. We're only going to go between, again, negative pi over 2 in order to pass that vertical line test. We're going to go from negative pi over 2 up to pi over 2, right? So again, the inverse sine and the inverse tangent will only ever give you answers back, right? The range, they'll only give you answers back somewhere between, on your unit circle, negative pi over 2, right, or 270 degrees, and pi over 2, or 90 degrees. Now, we want a nice smooth curve, though, so we're not going to call that 270 degrees. We would call it negative 90 degrees, right, between negative 90 and 90, or negative pi over 2 to pi over 2, so that we get one nice smooth line. We don't have to jump doing quadrant 1 and then jump all the way down to doing quadrant 4, right, the last part of the unit circle. We're going to use half the circle, but starting with those negative values. Cosine, on the other hand, again, it exists nicely from 0 to pi. So again, we'll get nice answers from 0 to pi, right, for the inverse cosine. So let's show you where that sort of helps you out. If you were finding or trying to look for values here, if I want to find the inverse cosine at root 2 over 2, again, I'm going to picture on my unit circle, root 2 over 2 makes me think 45 degrees. Right now we're in radians, so immediately I'm thinking pi over 4. So again, I would have a value at pi over 4 here. Technically, the cosine would also be a positive root 2 over 2, right, down in quadrant 4. But remember, cosine or inverse cosine only exists between 0 and pi, right? That first answer that we get is always between 0 and pi. It's kind of like the difference between saying, okay, well, what if we were trying to say, find the value of the square root of 4 versus find all answers to the question x squared equals 4. Well, over here, it's just 2. But if you're solving an equation, we would say plus or minus 2, right? We take the square root of 4, but again, we got to consider both positive and negative. Well, it's the same idea right now on our screen. I'm not saying solve the equation, right, when the cosine of x equals root 2 over 2. It's hinting toward it, but that's not really the question I'm asking. I just want the first value of it, right? Inverse cosine of root 2 over 2, just the one value. I'm not solving for all possible values, like solving an equation, right? I just want the first time that happens. So the first time it happens would be at pi over 4. Let's think that same way for the tangent. Again, the tangent technically is equal to 0 every pi units. It would be at 0, 0, right? And then we'd be at pi 0 and 2 pi 0. Or on our unit circle, it would happen at 0, it would happen at pi, and then we'd go back around to 0, right? We'd go around, and we'd hit another value and another value over and over and over again. But for us, right, remember that the inverse tangent and the inverse sine exist on the right side of our unit circle, negative pi over 2 to pi over 2, and the only time in that range that the inverse tangent equals 0 is at 0 radians. only time between, again, negative pi over 2 and pi over 2 is, again, when we were at 0 radians, right? Very simply. And then finally, same thing for the arc sine. Arc sine only exists on the right side. So where would the arc sine be a negative 1/2? Well, sine of 1/2, or sine of theta equal to a half, right, typically happens when theta equals 30 degrees. Right? So it would happen about here. Sine technically also would have been positive over in quadrant 2, but again on the right side, from negative pi over 2 to pi over 2, it's only going to happen, right, over here at pi over 6. It's only going to happen at that 30-degree angle. We're only going to get the one value. So again, it's always helpful to draw those circles. Now over here at the right, that will give you an explanation of if you were using your calculator. Notice these values inside of our inverse functions. These aren't the nice values like a half or root 2 over 2. Make me think of those special triangles. So I can just type these into my calculator. Now realize, again, I want to be in radian mode according to my directions. So make sure you're in radian mode. But if you did type them in, again, I can get positive values back. Sine and inverse tangent, they often give us negative values back. One thing I want to realize, again, if I think about my sine curve, sometimes those things will be undefined for the inverse function because I can't type a number in, right? Remember when we go back here, for the inverse sine, our domain is -1 to 1. I couldn't have a value outside of that -1 to 1 range for the sine. I can't put in a value outside of -1 to 1 for the sine or the cosine. Now I can for the tangent. Tangent, all real numbers, right? I can domain of all real numbers, I can plug in whatever I want. But for the sine, since -3.928 is greater than, or sort of outside the range of, right, the sine, it would be outside the domain of the inverse sine. That's not in the domain. Whereas for tangent, again, it definitely is. You can type in anything you want into the tangent, right? Put anything you want in there because, again, the domain is infinite, even though the range was limited, right? Negative pi over 2 to pi over 2. One last small hint for you. If you want to try to remember these sort of ranges of where you're going to get your values from, I always think of something simple called Santa's cap. Santa's cap. Santa, okay, has both an S and a T in it. And so therefore, Santa's cap, Santa's got a big belly, right? A bowl full of jelly. So again, sine and tangent are going to be sort of like Santa's belly. They're always on the right side of that unit circle. Whereas Santa wears a hat, right, or a cap. Okay. And cap starts with the letter C. Cosine is sort of like Santa's cap, right? It's above or on top of his head there. So again, sine and tangent on the right, cosine on the top. It helps me remember it. I hope it helps you. If you have any questions, make sure you talk to your teacher. Otherwise, have a great day.